All right. Thank you for the questions. And once again, thank you, Professor Kim Jae-suk, for the talk. We're going to continue to our next speaker. So allow me to introduce Professor Lim Shin-ll. Professor Lim, 안녕하세요. Professor Shin-ll has been teaching in Sejong University since 1995, researching areas in analog and mixed mode of IC design for communication, consumer, and sensor application. He was the chair of Technical Programming Committee International SOC Conference in 2009, and also the general chair for 2011. So we welcome you, Professor Lim Shin-ll, to deliver your talk called Bioelectronic Technologies for Increasing the Quality of Life. We're listening.
Okay, thank you for your kind introduction. Can you show the slide?
Yeah, we can see it, Prof.
Yes, clear.
Oh, let me check. Can you see my slide?
네, 잘 보입니다. 예.
네. 오케이. 알겠습니다. 네. Okay, good morning, ladies and gentlemen. Welcome, everybody. My name is Shin-ll Lim, professor of Sejong University in Seoul, Korea. It's my pleasure and honor to see you online and to share the recent technical trend of bioelectronics. Today, I'll talk about the bioelectronics technologies for increasing the quality of life. This is the outline of my talk. After brief introduction, I'll talk about 3 categories of bioelectronics technology. I'm going to start with some techniques on the biopotential signal detection. I will review what kind of biopotential signals are existed from the body and what kind of requirements are needed for the detecting circuit and so on. And then I'll take a brief look at some state-of-art research of implantable devices, such as Pacemaker and deep brain stimulation devices. After that, I briefly introduce biochemical sensor chip capable of performing DNA sequencing. This technique is not matured yet, but enabling genomic personalized medicine in near future, informed by an individual DNA. And finally, summarize my talk. Basically, I've been working on implementing and designing semiconductor chip for the interface circuit of these bio-related devices. But in this talk, I will exclude anything related to the circuit design technique, and I will focus on introducing technical concept, the principle of bioelectronics technology, and the requirements for implementation. This slide shows the cost of healthcare in some developed country. As you can see, the cost of healthcare is rapidly increased with the general process of treatment. As the human lifespans and the elderly people increase, the medical cost by chronic disease is also increased. WHO reported that over the last 40 years, the number of obese people has tripled. In the European region, for example, 1/3 of 11-year-old boys and girls are overweighted. This obesity causes many chronic diseases and make the quality of life worse. Populations are aging throughout the world. As you can see, the population over 65 is larger than the population under 5 globally. Korea also enters the age of aging. Korea is now declining birth rate and increasing the aging population rapidly. According to the Deloitte report, global healthcare spending is increasing at an annual rate of 4.1% between 2017 and 2021. They also forecasted that healthcare cost will be almost the same as the national one-year budget in the year of 2030. We are now living in the new wave of AI, IoT, and big data. By gathering the body signal regularly and continuously from handheld devices and also wearable devices, and by acquiring individual genomic information through small DNA sensor, biosensors, artificial intelligence with big data can predict individual outbreak of outbreak of illness, and can inform us about the personalized treatment. If your smartwatch detect your body signal, such as pulse rate and oxygen saturation rate, then detected big data goes into Apple server or Google Android server and filed up for a long time as a form of big data. AI can tell you customized and personalized information to you. People are looking for increasing their efficiency of healthcare because it's costing too much. So people can continuously looking for a new way to improve their existing healthcare with low cost and in a convenient and comfortable way. Fortunately, iHealthcare technology, including bioelectronics, AI with big data, are expected to favor new version of personalized and predictive healthcare with low cost. Since Professor Kim already talked about the AI-based diagnostic kit and AI-based therapeutic drug development, I will focus on the bioelectronics technologies. This slide shows the various body signals that can be detected from the body. For a little bit of background, I will start with electrophysiology. It's very difficult terminology. It turns out that most biological processes involve the flow of ions across cellular membranes. The human body is largely on the ionic system. Ions are charged particles, and therefore they generate electric field. I, as an electrical engineer, know how to measure electric field, and that is really the basis of electrophysiology. Now, if the ions move in the space, then they create current, and therefore they also create magnetic field. We should also be able to measure magnetic field. Predominantly, electrophysiology is focused on the external measurement. You can put electrodes on the surface of body and get rich information about the electrical function of a human body. We can also certainly do electrophysiology inside the body, but obviously it's more than invasive, and we only do this in very specialized cases. It turns out when you are measuring electrophysiology from external to the body, we are not measuring individual cells, we are measuring populations of millions of cells at once. There's a bunch of different type of electrophysiology measurement we can take. There is an electrocardiograms, ECG. This is electrical activity of heart. There is a EEG of the brain, EMG of the muscle, EOG of the eye, EGG of the gut, and so on. GSR is for skin conductance. BP means the blood pressure. PPG measures pulse and pulse rate by using LED or photodiode. Also measures oxygen saturation rate. Voices and images are also biosignal, but not in the range of biopotential signal. This slide shows the typical block diagram for biopotential detection system. Left side is energy source. It could be a harvested DC source from vibration or RF signal, or a DC converter with LDO. But anyhow, it provides the energy source for the device. In the right side, we can have data telemetry, which is used to control the device and extract data. Also, we have a user interface and data storage devices. In the center, body signal can be detected by transducers or sensors, which generated electrical signals such as voltage, current, resistance, and charge. And this detected electrical signal is amplified, filtered, and AD converted to signal processing for data analysis and system control. These measurement block usually implemented with a CMOS chip. Electroencephalogram, mean EEG, electrocardiogram ECG, and the electromyogram EMG waves are microvolt range signals, but have different amplitude and different frequency ranges as shown in this slide. ECG signal, we can see that voltage amplitude range from microvolt to maybe a couple of millivolts, and the bandwidth goes to maybe 250. You might think this is very easy to design since we design things at gigahertz. Designing something for 250 hertz of bandwidth is trivial, and you can think that it's easy to design low bandwidth things, but there are some difficulties to implement. First of all, of course, there is a noise. In fact, signal amplitude are pretty low, especially when we get the EEG kind of territory. Noise level is slightly larger than the EEG signal. We have flicker noise too. It's just from the CMOS transistor. We also have electrode offset voltages in low frequency area. They are basically DC, but they have perhaps a little bit slowly varying frequency contents. And we also have 50 or 60 hertz interference. This makes the whole space a little challenging. Again, you can see that EMG has the frequency range starting from 200 hertz up to 500 hertz. If you look at the EEG signals, the frequency can start as low as 0.5 hertz, and the signal frequency goes up to 200 hertz. To achieve signal extraction under these circumstances, front end, I mean the instrument amplifier, is needed with a high input impedance, high CMRR, common mode rejection ratio, and high pass filter characteristics for edge coupling and DC offset removing. And for system related issue, low noise, small size, and reconfigurability in gain and bandwidth for different biopotential signals are required. Furthermore, low power consumption is necessary to achieve long-term power autonomy. Multiple physiological signals can be supported in a chip. For example, in the previous slide, since the circuit blocks for EEG, ECG, and EMG are almost the same, they can share some same hardware, but the gain and bandwidth are reconfigured by application control. This chip implementation can reduce power consumption, chip area, and hardware cost. Handheld device such as cell phone can have optional devices for biosignal detection. This bioprocessor in cell phone can detect ECG signals, PPG, and body impedance, skin temperature, body temperature, and blood pressure. Wearable electronics has become mainstream, enabling personal healthcare technology in the form of patch, wristband, and smartwatches, making a reliable and sustainable measurement in the outside of traditional clinical setting is a real challenge. Wearable healthcare is not a new word. If you look around, you'll find tons of wearables in different form factors. For example, earbud, such as AirPod of Apple, patches, belt, or shoes. They can measure variety health parameters in your daily life. So from a market perspective, the wearable healthcare market is expected to reach more than $41 billion in this year. As I already mentioned, populations are aging throughout the world. The cost of healthcare keeps rising, right? So people are continuously looking for new ways to improve their existing healthcare with low cost and in a convenient and comfortable way. Wearable sensor can be a good solution for this. Sensor on the body can measure signals continuously, empower you to change your bad behavior and lifestyle to live healthier. Furthermore, they can manage disease and health conditions and reduce the number of days patients spend in the hospital. So wearable healthcare will link to the concept of outpatient monitoring or home healthcare. It is benefited from the advancement in AI and big data and IoT. The block of wearable devices include the blocks of a biopotential measurement system in the previous slide, but wearable devices have various energy harvesting source for powering and also have a wireless interface to communicate with server. This is the basic function for IoT applications. Multimode physiological and weak biopotential signals can be recorded with the help of one system chip that guarantees the robust and precise signal processing, even in the many difficulties such as noise, offset, and interference, etc. This high-level chip integration reduces the complexity of PCB, amount of components, power consumption, and the system cost of medical devices. And this bioelectronics technology enables to implement wearable and implantable miniaturized medical devices. Bioelectronics technology, including molecular biosensor chip, paved the way to perform predictive, preventive, and personalized treatment, and hence to increase the quality of life. Okay, let's move on to implantable devices. Here, I will show you some examples. First one is the pacemaker, which can regulate heartbeat. The second example is used for spinal cord stimulation. This can be used to treat patients that suffer from chronic pain who cannot be treated by traditional methods. The middle one is a cochlear implant, which has been very successful. The first one in the left bottom corner is a visual processes. This technology is not matured yet, but it could attract a lot of attention because it could really help people who are blind. They can be see again. Last in this slide is the deep brain stimulation device. It includes a metal can, which houses all the electronics and battery and reed. At the end of the reed, are the electrode, and these are responsible for interfacing with the brain. In this slide, some examples of therapy by micro-stimulation are displayed. Since these devices are implanted in the body, miniaturization and low power consumption are essential requirements. This is an X-ray of an implantable device. You can see that this can be implanted on the chest, and the wire for the reed is run underneath the skin and to the back of the ear and to the top of your skull, where it's possible to drill a hole and insert the electrode into a deep area of the brain. With these deep brain stimulation devices, the patient who suffer from tremor or Parkinson's disease can be relieved of their symptoms. A cardiac pacemaker is used to treat arrhythmia, or heart rate is too slow, and cardiac arrest. This device monitors the heart rate, how fast it beats, and also heart rhythm, the pattern in which it beats. And it provides electrical stimulation when the heart does not beat or beat too slowly. It's typically small in size and often less than an ounce in weight and less than 2 inches wide. Cardiac pacing devices, pacemaker, are the almost common implantable biomedical device on the market. Several factors contribute to the success of pacemaker, among which size, and battery longevity. The pacemaker system, as shown in this slide, consists of two components, pacing lead and pacemaker device. The pacing lead connects between the heart and the pacemaker device. It is flexible, insulated wire with an electrode tip. This tip, inserted through the vein in the heart, carries impulses from the pacemaker device to the heart and stimulating the heart to beat. Battery, PCB, and chips are sealed with titanium can housings. Low power consumption is essential in circuit design to guarantee the minimum 10 years of operation with one battery. So the most transistor in the chip is operated in the sub-threshold region. Let's look at the comparison between the pacemaker and the neuromodulation device. I mean the deep brain stimulation devices. The pacemaker detects the heart information, will do the analysis in time domain to detect P, R, T signals to determine whether a bit is missed or not. If you detect a missed bit, then the stimulation will be delivered and it will trigger a heartbeat. For the neural stimulation devices, it's slightly different. The signal has to go through spectral domain analysis, like FFT operation, to extract spectral information from the deep brain. For example, we get the energy information at a given frequency band and potentially use that to close the loop for stimulation. This slide shows the simplified diagram for implantable devices that include 5 parts. For the top is the energy source. It can be a primary or a rechargeable battery, or it could be an RF power source with a supercapacitor. But anyhow, it provides the energy source to the devices. Then you have data telemetry, which is used to control the device and extract data. At the bottom is the nervous system. We have to have a way to interface with the nervous system, both for sensing and for stimulation intervention. This part is mainly different from the block diagram of biopotential measurement system in previous slide. Between them is the signal processing for data analysis and the system control, and it can be implemented in our SoC1 chip. Since the device is built in the body, it should be small and biocomfortable. Safety and stable operation are essential requirements. Okay, next topic is the biosensor. Quantitative and specific detection of biomolecular, such as DNA and proteins, have numerous applications in biomedical diagnostics and individual monitoring. DNA sensing, in particular, has broad application in genotyping, gene expression studies, biohazard detection, drug discovery, and so on. Over the past 3 decades, we have witnessed substantial progress in DNA sequencing method, leading to significant acceleration in medical research and discovery. Biochemistry sensor chip technology is pushing closer to our homes by enabling genomic personalized medicine, in which healthcare is informed by an individual DNA. There is a DNA sequence, a sequence of adenine, thymine, guanine, and cytosine determines the DNA structure. DNA is structured by the sequence of complementary chain, as shown in the left side. There we have a specific binding of adenine thymine pair and also guanine cytosine pair. In general, DNA microchip is slide made of glass, a polymer material, silicon, etc. On the surface of such a chip, single-strand DNA receptor molecules, probes, are immobilized at a predefined position. These probe molecules consist of different DNA sequences, whereas a number of different techniques are known to functionalize the chip. In this figure of left, two different sites within an array are considered after the immobilization phase. Spot different single-strand DNA sequence on the different position. After that, as shown in the figure of center, the whole chip is flooded with a sample containing a target molecules. In case of complementary DNA sequence of probe and target molecules, their match lead to a hybridization as shown in the right top. If probe and target molecule mismatch, this chemical binding process does not occur as in the figure of right bottom. After a washing step, double-strand DNA is obtained only at the matching position. At the mismatch site, single-strand DNA molecules remain, and the same situation as in the initial case of left side. Since the receptor molecules are known with the label, the information where double or single-strand DNA is found at the different test site reveals the composition of the sample. Thus, the requirement contains to identify the site with double-strand DNA. In conventional systems, the target molecules are usually labeled with the fluorescent markers, and an optical image of the array chip reveals the position with the double-strand DNA. But this kind of detection system needs optical devices, which makes the system bulky, so the system slow and very expensive with large power consumption. A single sensor site consists of interdigitated gold electrode on the CMOS chip. Probe molecules are immobilized on the gold surface. The target molecule in the sample are targeted by an enzyme label. After hybridization and washing phases, a chemical substrate is applied to the chip. At the position with matching DNA strand, the enzyme label cleaves to the phosphate group and generates an electrochemically active compound. Applying simultaneously an oxidation and reduction potential to the sensor electrode, about several hundred of millivolts with respect to the on-chip reference potential, the oxidation and reduction process generates currents at the electrode. A potentiostat whose input and outputs are connected to the reference and to a counter electrode respectively, provide the difference current to the electrolyte and regulate the potential of the electrolyte to a constant value. As shown in the previous slide, the electrochemical bio sensor transduced between the ions and the electrons. This is typically done by measuring electrons through the electrochemical reduction and oxidation reactions. There we have three main cases of electrochemical biosensors. This is the potentiometric. There is a potentiometric biosensor. This effectively just measure open circuit voltages. And there is a amperometric sensor, which effectively measure current, as in the previous slide. And there is a electrical-chemical impedance spectroscopy sensors that measure complex impedance. This slide shows another example of electronic sensing in biochip. The circuit measures capacitance variation due to DNA hybridization on the gold electrode, which are bio-modified by covalently attaching proofs of known sequence. This work was fabricated with the standard CMOS technology with one additional step for gold deposition. Some company like Insilixa announced the commercial product sensing with the CMOS image sensor. It was small, fast, and disposable, but there is a limited reaction applications. This biomedical technology in the form of single-use disposable chip provide performing medical diagnostics and DNA sequencing, and the use of scalable CMOS chip architecture allows radical levels of economic scaling and provide convenient new format of diagnostics and predictive and personalized medical services. Okay, with the help of bioelectronics, as I mentioned in this talk, also with the help of AI, IoT, and big data, we can change the conventional medical treatment to predictive and personalized medical services. This technique is not matured, but it rapidly developing. There are many obstacles to overcome. It's really worth challenging. Okay, here we have a summary. Multimode piezo signals, physiological and weak biopotential signals can be recorded with one system chip. High-level chip integration reduce the complexity of PCB, amount of component, power consumption, and system cost. And hence enables wearable and implantable miniaturized medical devices. These miniaturized medical devices enable people to increase the quality of life. Moreover, bioelectronic technology, including molecular biosensor chip with AI and big data, paves the way to predictive, preventive, and personalized treatment. Okay, thank you for your attention.
All right, thank you, Professor Lim Shin-ll.
Yes.
That was a nice